of May 1919, a total eclipse of the Sun passed over the southern Atlantic. Two expeditions headed by British astronomers Arthur Eddington and Frank Dyson set off to observe this phenomenon. One team headed to Brazil, the other to West Africa. The expeditions were beset by problems, from faulty instruments to weather that refused to cooperate. On the island of Principe, off the coast of Africa, the eclipse was due at 2 p.m. But throughout the morning, Eddington had sat in the pouring rain, the sun not peeking from behind the grey until half an hour before the eclipse. Clouds continued to cross the sky even as it darkened. Eddington busied himself changing photographic plates in the telescope, only glancing momentarily at one of nature's most spectacular sights. Would the observation be a lost cause? Would all this effort be a waste of time? A few days later, Eddington had his answer. And our picture of the universe changed forever. The headline in the New York Times proclaimed "Lights all askew in the heavens," and the little-known Albert Einstein became the most famous scientist in the world. 4 years earlier, during the turbulent years of the First World War, Einstein had published his general theory of relativity. The culmination of a decade's hard work, relativity gave us a new picture of gravity, replacing Newton's forces with malleable space-time. During the war years, relativity was an academic curiosity, but with peace restored, scientists had set out to test the predictions of this new scientific theory. Their goal had been to measure the locations of background stars, whose light passed close to the edge of the sun, stars that would be visible when the immense glare of the sun was dimmed during an eclipse. If Einstein was correct, the gravity of the sun should act like a lens, gently deflecting the starlight from its straight-line path. And on the photographic plates obtained in Brazil and Africa, the stars had shifted by the predicted amount. Einstein's theory had triumphed. Whilst the result made him a star, Einstein thought that this gravitational lensing had little practical consequence. Stars were simply not massive enough to use as natural telescopes to magnify the distant universe. Nothing could be. There was nothing in the universe with enough mass to have such an effect. Or at least, as far as he knew. In the 1930s, astronomer Fritz Zwicky was working at the California Institute of Technology. Zwicky was a brilliant scientist with a prickly personality. Combining geometry and profanity, he referred to his enemies as spherical bastards, implying they were a bastard no matter which way you looked at them. But as an original thinker, Zwicky's mind roamed through the mysteries of the universe. He coined the word supernova to describe immense stellar explosions, and realized a superdense remnant known as a neutron star would be left in the ashes. And in 1933, Fritz Zwicky was focusing on the Coma cluster. Located 300 million light-years away, Coma is immense and home to thousands of individual galaxies. This was barely a decade after the realization that the Milky Way was not alone in the universe, and numerous other galaxies exist, scattered throughout the cosmos. Zwicky reasoned that the individual galaxies in Coma were held in their orbits by the gravitational pull of all the other galaxies around it. He realized that by measuring the galactic speeds, he could determine just how much mass was in the Coma cluster, providing a new way of weighing the galaxies. But instead, what Zwicky found was a big problem. The galaxies in the Coma cluster were moving far too fast. With only the gravitational effect of the galaxies in play, each galaxy in Coma should have been traveling sedately in its orbit. With immense speeds of almost 1,000 kilometers per second, Coma should have been tearing itself apart. It was clear significantly more gravity was needed to hold Coma together. What was the source of this extra gravity. With nothing obvious, Zwicky concluded that there must be dunkel materie, dark matter, gravitationally binding the Coma cluster. And there had to be a lot more dark matter than the stars we can see. Zwicky's realization that much of the mass in the universe is dark was startling. Questions immediately sprung to mind. How much is there? What is it made from? And how can we measure it? Zwicky's discovery should have set the astronomy world on fire. But instead, there was silence.
Passwords remembered for you. There's no place like Chrome.
Want to know how to find the cheapest flights on Kayak? Head to Kayak, enter your origin and destination. Choose your preferred dates and how flexible you are with them. And there you have it. You can pick the cheapest flights from a whole range of dates. Start planning your journey with Kayak. Head to kayak.co.uk now.
Possibly because of his brusque style, this notion of dark matter lay buried in the pages of scientific journals. And for the next few decades, astronomers had a new focus: measuring the expansion speed of the universe. By the 1970s, there were new technological advances, large telescopes, and sensitive instruments for observing the heavens. And with these, a new generation of astronomers was asking new questions about the universe. For Vera Rubin, the target was large spiral galaxies similar to our own Milky Way. Working with her collaborator Kent Fort, Rubin wanted to understand how these galaxies spin. She had entered astronomy when it was essentially a male-only activity, and she encountered resistance throughout her career, including a lack of female bathrooms in the telescopes she used. But this didn't stop her, as she undertook meticulous observations of the rotation speeds of spiral galaxies. The expectation was that these galaxies were like the solar system, with most of the mass concentrated towards the center. Just like the planets, the speeds of stars in the spiral disk were expected to fall as gravity gets weaker towards the edge. But this was not what Rubin found. The rotation speed of stars did not diminish, but remained roughly the same all the way to the edge of the galaxies. Just like Zwicky, Rubin was left with a gravitational puzzle. What was the source of gravity needed to keep the stars moving at their unexpected speeds? Zwicky's dark matter was back in the spotlight. It was becoming clear that what we could see with our telescopes, the myriads of stars and clouds of gas, were nothing but minor cosmic players. Astronomers were faced with a stark question: is there an entire shadow universe of dark matter out there? The evidence was growing, and it was now they turned to Einstein's seemingly inconsequential theoretical prediction made more than half a century before. They turned to gravitational lensing. Indeed, Zwicky had suspected this also years before. He had reasoned that with the extra dark matter, galaxies and clusters of galaxies would be powerful gravitational lenses. But it took until the 1960s for scientists to really come to grips with this concept and find a point of energy staggeringly huge enough to properly observe. Quasars. Appearing as little more than points of light through the most powerful telescopes, they shine with the brightness of more than 100 trillion stars. It was realized that quasars were powered by supermassive black holes. The gravitational pull of these black holes accelerates infalling material to close to light speed. As it swirls into the inner regions, matter crashes together, heating it to immense temperatures. And it is this accreting disk of matter that glows so brightly. And with this immense brightness, astronomers could spot quasars at incredible distances, many billions of light years from Earth. By the 1970s, with their observational approaches honed, finding quasars was routine. Then, in 1979, one quasar, uninspiringly labeled Q0957+561, provided a puzzle. Astronomers realized that this appeared to be two quasars very close to each other in the sky. This is not too unusual, but it was found that these two quasars appeared to be identical. The astronomers realized that they were seeing double, a gravitational mirage. Between us and the quasar sits a massive galaxy, and its gravity distorts our view, producing two separate images of the single object. Zwicky was right again, and more than 80 years since it was first observed under the clear skies of Africa and Brazil, gravitational lensing had found its purpose. In the decades that followed, thousands of gravitational lenses have been discovered. Many of these are due to individual galaxies, but the most spectacular are produced by the immense gravity of gravity clusters. Distant galaxies that would be too faint to see in our telescopes are magnified by these cluster lenses, appearing as immense arcs. Every instance of gravitational lensing provides an opportunity to measure how much mass is present by measuring the distortion. And the conclusion is always the same.